Welcome to the video lecture on the law of sines. We have used trigonometric functions to solve right triangles using the right triangle definition of all of our 6 trig functions. We will now learn how the trigonometric functions can be used to solve oblique triangles, which are triangles that don't have right angles in them. There are 2 relationships that can be used depending upon the information that is known about the triangle, the law of sines and the law of cosines. In this lecture, we're going to talk about the law of sines, which says that the lengths of the sides in a triangle are proportional to the sines of the angles opposite these sides. When we talk about oblique triangles, we're going to use this standard labeling system, and these can be acute or obtuse triangles. This one would be acute, where all the angles in the triangle are smaller than 90 degrees, or this would be an obtuse triangle where at least, well, not at least, exactly one of the angles would be greater than 90 degrees. And the way that we label these in a standard way is to label the vertices of the triangle as capital letters and the opposing side as lowercase letters. So angle A and its side opposite would be little a. Angle B, side opposite little b. Angle C, side opposite little c. So you will see that notation quite often in this lecture today. Now let's prove the law of sines first before we start using it. So here is just a generic oblique triangle. Sides little a, b, and c, and angles capital A, B, and C. And we know from a previous lecture that there are ways to find the area of this triangle if all we know about it are the 3 sides and the 3 angles. Namely, there's a formula that says that the area of your triangle is 1/2 the product of 2 sides times the sine of the angle in between. So, for example, we could say that the area of triangle ABC is equal to 1/2 this side A times this side B times the sine of the angle in between, which would be angle C. Now, what if I had chosen to find this area in a different way instead? What if instead I had used these 2 sides over here, side A and side C? So then the area would be 1/2 side A, side C, and the angle in between those 2 sides is angle B. So this would be sine of angle B. A third possibility would be to say that the area of triangle ABC must be 1/2 these 2 sides, so side B and side C, times the sine of the angle in between, which is sine of angle A. Now, since all 3 of these formulas are all calculating the area of this triangle, then all 3 must be equal, because there's only one area for this whole triangle. So what that says is that 1/2 AB sine C must equal 1/2 AC sine B, and that must equal 1/2 BC sine A. Now, to simplify this or rewrite it in a different way, what I'm going to do is I'm going to multiply all 3 parts of this sort of double equation here. I'm going to multiply everything by 2 over ABC. So I'm going to multiply by this expression 2 over ABC. Now, if we do that for this first one, the 2's are going to cancel out, the A and the B are going to cancel out, and what we'll be left with is sine C on top and this little c on the bottom. And if we go to this one in the middle and I multiply by 2 over ABC, again, the 2's are going to cancel, the A's are going to cancel, the C's are going to cancel, and we're going to be left with sine B over little b. Okay, so for this third factor, what we'd see is the 2's will cancel out, the B and the C will cancel out, and we're left with sine of angle A over little a. And this is the result called the law of sines. So what it says is the proportion of the sine of an angle over its opposite side, those must be in proportion to each other. So we're going to use this to help us solve oblique triangles. Now, before we get to using it, let's talk about when would be a good opportunity to use it. So in general, A triangle can be considered solved if we know 3 of the 6 parts, except for the case of knowing all 3 angles, because this does not define a unique triangle. So here's various possibilities that you might see. You might have side angle angle or angle side angle, so where you know one side and 2 angles. You could know 2 sides and 1 angle, and in this case the angle would have to be opposite one of those 2 sides. You could know side angle side, so 2 sides and the included angle, or 3 sides. So let's look at pictures of what these would look like. So side angle angle is when you know one side, and that's this blue side over here, and 2 angles, where one of the angles would be opposite that side. These 2 sides in red would be the sides we don't know. Another possibility, just a different configuration, is if the side that you know is one of the sides that forms these 2 angles. So you've got angle, side, angle. So the side is sort of in between the 2 angles that you're using. Another possibility is side-side angle. So here you know these 2 blue sides, and you know one of the angles that's across from one of the sides. Now these 2 cases, case 1 and case 2, where you either know 2 angles in one side or 1 angle in 2 sides, these are going to be the cases where we're going to use the law of sines. This second case, and we will explore this in just a minute, is called the ambiguous case, because sometimes it leads to more than one possible triangle existing for this situation. In these cases up here, you would only have one possible triangle. The third and fourth case, where you have side angle side, so the 2 sides and the included angle, or knowing all 3 sides, these are going to be the cases where we're going to use what's called the law of cosines, and that's going to be discussed in another lecture. So in this lecture, you are going to see cases where you know 2 angles and a side, or 1 angle and 2 sides. So let's take a peek at that ambiguous case. You can see that a unique triangle is formed in these situations. However, in the second case, that side-side angle case, there may be 2 triangles with the given properties, 1 triangle or possibly no triangles at all. For this reason, this situation is referred to as the ambiguous case. We're going to sketch the different possibilities that can show you how you might end up with 0 triangles, 1 triangle, or 2 triangles for this side-side angle. So if you have side-side angle, given side A and side B, and angle capital A, here would be a picture of a possible case where you might have no triangle at all. This height here, H, is the perpendicular height that you would need to ensure that you have a right triangle. So I'm going to compare this side A to this perpendicular height H. If the side A is smaller than that perpendicular height H, then that means that side A is not going to be quite long enough in order to touch the bottom down here and form a triangle. So if that happens, then you would have no solution. You would have no triangle. If this side A is exactly the same as the length of H, then you will get exactly 1 triangle, and it will be a right triangle. So that's one way to get 1 triangle. If this side A is smaller than B, that's what I meant to say, smaller than side B, but greater than this perpendicular height H, then this is kind of our 2 triangle situation. You could either angle that side A a little bit down to the left or a little bit to the right, and it would still touch down, and you would get 2 different triangles being formed. So you would either have this triangle right here, which would be an oblique triangle, or you would have this triangle over here as well. So you'd have an obtuse angle over here, because this angle would probably be obtuse, versus the bigger one, which would be acute. And then finally, if your side A is much larger or just bigger than side B, then you're going to have this big side coming over here, and there's only going to be 1 triangle possible. So depending on what side A is in relation to side B and in relation to this perpendicular height, you could have either 0 triangles, 1 triangle in these two cases over here, or possibly 2 triangles. So how do you know which case it is? Well, it's kind of tricky to remember those 4 different possibilities. So what we're going to do is, instead of relying on those sketches to help determine which case we are, we're just going to go about solving the problem, find our angle A, and then we're going to consider using not just that angle A, but also its supplement. And if that creates 2 possible triangles, then we will have 2 solutions. If it's not possible to find that angle A, then we'll have no triangle. And if we find the angle A and its supplement doesn't exist, then we'll only have 1 triangle. So you will see examples of this coming up in just a second. So here's a typical example. We are given angle A is 40 degrees, angle B is 60 degrees, and side A is 4. So you want to draw a picture for this. Remember that capital A is the angle, so its side opposite would be little a, which is this 4. So no matter how you draw your triangle, make sure that you put this angle 40 degrees in one corner, and the side opposite must be that 4 side, because that's your little a. So if we look at what we have here, we know 2 angles and one of the sides opposite those angles. So this is an SAA case. Okay? So we know 2 angles and we know the side opposite it. So if you know 2 angles, then you automatically should know what the third angle is, and that's because you want to remember that all 3 angles in a triangle always have to add to 180 degrees. So 40 degrees plus 60 degrees plus angle C has to equal 180 degrees. 40 plus 60 is 100, so that forces angle C to be 80 degrees. So now we know that this angle right here must be 80. So we know all 3 angles. Now to finish solving this triangle, we know all 3 angles, we need to know all 3 sides. So I need to find side B and side C. So this is where that law of sines is going to come into play. We are going to take the sine of the angle and the opposite side that we know both of. So in other words, I know angle A and I know side A. So that's the sort of starting point that you want to begin with. So according to law of sines, sine of that 40-degree angle over its opposite side 4 would have to equal sine of one of the other angles over its opposite side. So you could, if you wanted to solve for side B, you could do sine of 60 degrees over its opposite side B. Or you could do sine of 40 degrees over 4. You have to use that pair that go together, and you could look at sine of 80 degrees over its opposite side C. And these are both of the things we're going to need to solve if we want to find side B and side C. So these are the 2 proportions that we're going to set up. Now how do you solve a proportion? Easiest, quickest way to do it is just to cross multiply. So that's what I'm going to do. So I'm going to multiply B over to the left side, and this becomes B sine of 40 degrees. And on the right side, when I multiply that 4 across, I get 4 sine of 60 degrees. And we're trying to solve for B, so I want to divide both sides by 40 degrees, sine of 40 degrees. So B is going to equal whatever 4 sine of 60 over sine of 40 is. And when we type this in our calculator, make sure you use parentheses around that numerator. Similarly, I'm going to cross multiply on this proportion as well and do exactly the same steps. So this will become C sine of 40 degrees equals 4 sine of 80 degrees, and to solve for C, I'm just going to divide by sine of 40. So C will be whatever 4 sine of 80 degrees over sine of 40 degrees turns out to equal. And we're going to punch that into the calculator in just a moment, but one last comment before we pull up the calculator. Remember, this was the SAA case, and if you remember from earlier on, In the SAA case or the ASA case, there's only going to be one solution. If you know two angles already, then there's only going to be one triangle possible. The ambiguous case is when you only know one angle and you know two sides. So if we know two angles, then there's only going to be one case. And we won't have to worry about looking at possible alternative solutions. So once we find B and C, we'll be finished with this problem. So let's pull up the calculator. First thing you want to make sure of is what mode you're in. The angles that we are given in this problem are in degrees, so make sure you're in degree mode. And then we're going to go ahead and type in our proportions. So the first one for B was parentheses, and I wanted 4 sine of 60 degrees, close the parentheses on the sine, close the parentheses on the numerator, and then we're going to divide that by sine of 40. And I'm going to hit enter. And there's side B, about 5.39. Meanwhile, let's go ahead and find side C, which is exactly the same command that I just put in, but I'm going to edit it and change this 60-degree angle to 80 degrees and hit enter. So there's side C, about 6.13. So B is 5.39 approximately, and C is approximately 6.13. So we now know all three sides, and we now know all three angles, so we have solved this triangle. Okay, next example. Again, we know two angles. Angle A is 35 degrees, angle B is 15 degrees, and side C is 5. So since side C is opposite angle C, that means this is angle side angle. And if you know two angles, then this is only going to have one possible solution. This is not the ambiguous case. So we're not going to have to worry about checking different possibilities. So if we have two angles, you automatically have to know what the third angle is because all three angles have to add to 180. So again, 35 degrees plus 15 degrees plus angle C has to add to 180 degrees. So if we add 35 and 15, we're going to get 50, and when I subtract that to the other side, we get angle C is 130 degrees, which is an obtuse angle, which looks good with my picture here, the way that I've drawn it. Now, because I now know angle C, that means I have a pair that go together. I have an angle and its opposing side that I know both of the values for. So that's the starting point of your law of sines proportion. We know that angle 130 degrees goes with side 5. So using our proportion, sine of 130 degrees over the opposite side 5 has to be, if I wanted to find side A, then I would use sine of angle A, which is 35 degrees, over little a, or I could do sine of 130 degrees over 5, again that combination that I know goes together, is equal to sine of angle B, which is that 15 degrees, over side B. So these are the two proportions that I'm going to need to solve, and I'm going to do them by cross multiplying. So I'm going to get A sine of 130 degrees equals 5 sine of 35 degrees. And then if I divide both sides by sine of 130, we're going to get our value for A. Then I'm going to do exactly the same thing to get side B. So cross multiply gives me B sine of 130 equals 5 sine of 15, and divide both sides by sine of 130. And I'm not going to bother showing you how to type that into your calculator. It's exactly like how we did the last example, I'm just going to go ahead and tell you what decimals we get here. And these would just be approximations. So A should turn out to be approximately 3.74, and B turns out to be approximately 1.69. Okay, so this was ASA, and the earlier example we did was SAA. So both of these we knew two angles and one side, so we were able to get exactly one solution. The next few examples that we're going to do are the ambiguous case. So this time I'm only giving you one angle and two sides, and so there are different possibilities. You could either have 0 triangle, 1 triangle, or 2 triangles. So let's take a look at this example here. We know side A is 3, side B is 2, and angle A is 40. So no matter how you draw your triangle, wherever you place that angle A of 40 degrees, which I put in my left corner over here, the side opposite has to be this 3, since angle A and side A go together. So I'm going to put my 2 over here, so there's your little b, so angle B is in this corner, and angle C and side C are opposite as well. So this time I only know one angle, so we're not able to find these other two angles immediately like we were in the last case, because we knew that the sum of all three angles was 180 degrees. So here the only place to kind of jump in with is to note that I do have this combination of a side and an angle that go together. So I'm going to set up my law of sines to be sine of that 40 degrees over its opposing side, which was 3. So that's one part of that proportion that I automatically know. On the other side of this, there's only one good choice here, because I only know side B. I don't know angle B, and I don't know angle C or little side C. So you certainly wouldn't want to use C here and do sine of C over little c, because then that would have too many unknowns. But if I do sine of capital B over 2, then that only has one variable, so we should be able to solve this for angle B. So that's where we want to start. And again, we're going to cross multiply here. So if I do that, I'm going to get 2 sine of 40 degrees equals 3 sine of B. Let's isolate that sine of B by dividing everything by 3. And this tells me what sine of B is. So how do I get just a B? Well, you have to undo that sign, which is an inverse sign. So we're going to need to use that inverse sine button, and whenever you're using that, it should be telling you an angle. Okay, and we want to be in degree mode here because we're using 40 degrees. So whatever answer we get when we plug this in our calculator is going to be in degrees as well. So let's pull up the calculator and figure out what this tells us. So we want to do inverse sine of, and I'm going to use parentheses here again. In the numerator, I had 2 sine of 40 degrees, close the parentheses on the sine, close the parentheses on the numerator, and then we're dividing that by 3, and it's that entire quotient that we're taking the inverse sine of. So when I hit enter, this should be the value of angle B in degrees. So angle B is 25.37 degrees. Now when I do that, we also, because this is the ambiguous case, we also want to consider the other possible angle that might work, which is always going to be the supplement of this answer that you just got. So there's two angles where the sine of it is going to give you that decimal 2 sine 40 over 3. There's the angle 25 degrees, but also the supplement of that angle would also give you that same decimal. So a quick easy way to get your supplement is just to do 180 minus this answer that we just got. So 154.62, and that's a legitimate angle in a triangle because it's smaller than 180 degrees. We still don't know for sure if it's actually going to work as a solution, but it is a legitimate angle that might exist because it's smaller than 180. So both of these answers, 25.37 and 154.62, both of those are potential candidates for what angle B is going to equal. So we're going to need to write down both of them and work from there to see if both of them actually work. So let me quit out of my calculator and then I'll show you where to go from here. So the two cases we got were B is either 25.37 degrees. Well, let's just go ahead and round that to 0.4 just to make our lives a little bit easier. So 25.4 or 154.6. So those were my two cases. So what I'm going to do now is consider what might happen in those two cases. So let's go over to here. If B is equal to 25.4 degrees, let's figure out what angle C would then have to equal. So if we know that this angle right here is 25.4, we now know two angles, we should be able to find the third. So angle C would have to be 180 minus 25.4 plus 40. So 180 minus the other two. And if you punch that into your calculator, you get that angle C then would be 114.6 degrees. So if B is 25.4, then angle C would be 114.6. I'm going to come back to this in just a moment, but let's go ahead and see what would happen if we use the other choice for B. So what would happen if B was 154.6 degrees? What would that force angle C to be? So let's suppose that this instead was 154.6. Then angle C would have to be 180 minus 154.6 plus 40, the sum of the other two. And you can see that that won't work because 154.6 plus 40 is already over 180 degrees. So this is something negative. It's actually negative 14.6. So that can't happen because that would force angle C to be a negative angle. So that's how we know that even though 154.6 is a legitimate angle in a triangle, it forces the other angle to be too small and not make sense. So we're not going to have two cases anymore, we're only going to have the one. Now what do we know? We know then that this angle is 25.4, and now we know that this angle here is 114.6. So we have all three angles. The last thing we need to figure out is this missing third side. We still don't know what little side C should equal. So what we're going to do is use the law of sines again to figure out what side C should be. So I can do sine of, you could do 25.4 over 2. I tend to always go back to the original values in the original problem so that I'm not using estimated values or things that I've approximated, and 25.4 is just a decimal approximation. So I prefer to use sine of 40 over 3 since those are exact values, and that's one part of my proportion. And then in order to find side C, I can now do sine of 114.6 and divide that by side C. And then we're just going to cross multiply. So C times sine of 40 equals 3 sine of 114.6, and I just divide both sides by sine of 40. And when you do that, when you punch all of this into your calculator, what you end up with is that C is approximately 4.24. So we now know all three sides and we know all three angles. Okay, so this was that ambiguous case where we only had one solution. It wasn't the right triangle solution, but it was one triangle only. So let's go ahead and take a look at another example. So in this one we are given side A is equal to 6, side B is equal to 8, and angle A is equal to 35 degrees. So wherever you draw that 35-degree angle, the side opposite it needs to be the 6, since capital A and little a go together. So these are opposite each other. And I also know side B, so I'm going to put that opposite angle B. So it's very similar to the picture that we drew for the last problem. We are given a side, and an angle. So it's this SSA again. So this is that ambiguous case with potentially more than one triangle possible or no triangle possible. So let's see what happens here. There's not enough information to find your two angles immediately, so in order to find one of these angles, we're going to need to use that law of sines. So I'm going to do sine of big A over little a, since that's the combination that I know goes together. So sine of 35 degrees over 6, and I'm going to find angle B first because I know what side B is already. So sine of capital B over 8. Then we're going to cross multiply and get 8 sine of 35 equals 6 sine of B. Divide by 6. And that's what sine of B is equal to. So to get just B, I need to take the inverse sine of this quotient. So we're going to need to pull out the calculator again to figure this out. Okay, so what we need to type in here is inverse sine of, and I'm going to use parentheses for that numerator just to be careful here, 8 sine of 35 degrees. Close the parentheses for the sine, close the parentheses for the numerator, and then we're dividing all of that by 6. Close the parentheses for the inverse sine, and when I hit enter, this should be what angle B is equal to, or at least one possibility for angle B. Now remember, in the ambiguous case, once you find that very first angle that you're looking for, you need to find its value, but you also need to find its supplement. And both of those are potential candidates for what that angle B could equal. So while I have my calculator handy, let's go ahead and find the supplement. 180 minus this answer. So angle B could either be 49.89 or 49.9, let's round it off to 1/10, or it could be 130.1 degrees. So both of these need to be written down as possibilities. Once we know what B could equal based on these two choices, we're going to then see if both of these would enable C, angle C, to exist as well. Alright, so let's do that next. So angle B is either 49.9 degrees or 130.1 degrees. So first case, if angle B is 49.9 degrees, what does that force angle C to equal? Well, it would be 180 minus angle B and angle A added together. And if you punch that into your calculator, that is going to give you 95.1 degrees, which is valid. Okay, as long as it's not negative, then this triangle will exist. Alright, let's look at our second possibility. If angle B is 130.1 degrees, then angle C would be 180 minus angle B plus angle A. And this should work because 130 plus 35 is 165, so there is still room for angle C to be a positive angle. And if you punch this in, you end up getting 14.9 degrees. So this is going to have two triangles, because when I used angle B, I got a legitimate angle C, and when I used the supplement for angle B, I also got a legitimate angle for angle C. So as long as C is positive for both of these, then you're going to get two solutions. All right, so if we use this first case, let's go back to this first case. If this angle here is 49.9 and this is 95.1, we now need to use that information to still find this missing third side C. So the proportion that I would want to set up would be very similar to the first one we set up, sine of 35 over 6, but this time I'm going to use angle C. So sine of 95.1 over side C, cross multiply, divide both sides by sine of 35. Whoops, this should be a 6. And then if I do that, we get C is equal to whatever this is typed into your calculator, and that is approximately 10.42. Okay, now in our second case, let me draw my second triangle over here. We still had A was 35 and its opposite side was 6. We had side 8 for B, but this time in the second case we were assuming that angle B was 130.1, and my picture obviously is not to scale because that would be an obtuse angle, and this would be 14.9. So if we wanted to find side C here, then we would have to set up the proportion sine of 35 over 6 is equal to sine of this new angle C, 14.9, over C. And if I cross multiply, and divide both sides by sine of 35, you end up with C equaling 2.69. So these are your two triangles, this one and this one. Okay, and both are valid solutions because all three angles were positive and smaller than 180 degrees. Okay? All right, let's try one more example of this ambiguous case. So this time we have side A is 2, side C is 1, and angle C is 50 degrees. So again, we're given a side, and an angle. So this is SSA. We're only given one angle. But this time the angle C is given to us, so its opposite side, little c, should be 1. So however you draw that, make sure that the 50 degrees is opposite the side 1. And that's going to be our starting point for finding some of these other angles. So using the law of sines, the sine of angle 50 degrees over its opposite side 1 has to equal, now which pair should I use? I don't want to do sine of b over little b because I don't know either one of those values, but I do know side little a. So if I do sine of angle A over 2, then that gives me enough information that I can solve. So if we cross multiply, we get 2 sine of 50 degrees equals 1 times sine of A. And to solve this for A, I have to undo that sine, so I would need to do an inverse sine of 2 sine 50 degrees. So we need to pull up the calculator and punch that in. So inverse sine of 2 sine 50 degrees. And look at what happened. I got this thing that says ERR domain. That stands for error. And just to make sure that I typed it in correctly, I've got all my parentheses in place. So everything looks good, except when I hit enter, I get this domain error. And what that means, if we look back at our expression here, is that 2 sine of 50 degrees, I can't take the inverse sine of that because that ends up being too large. So that means that this does not have a solution. So this does not exist. Angle A does not exist. It's too big. It doesn't, the 2 sine of 50 degrees is too big to take the inverse sine of it. So this has no solution. which means we don't have a triangle. And just to kind of show you a better picture to demonstrate what's really happening here, if you wanted to draw this more like the ones we did earlier with our different cases, if we put this 50 degrees here and we put our side 2 over here, which was in this case the side A, and the side C should be opposite 50 degrees. What's really happening is this side C, which was only 1, is too short to reach the ground. It's too short to construct a triangle, which is why there's no triangle and there's no solution. So in this SSA case, when you're only given one angle and two sides, there can either be no triangle, which will happen whenever you try to find that first angle, you're going to get an error message on your calculator, or you could have only one solution, like this case here. You still need to find that first angle and its supplement, but when you go to find the third angle, that third angle will turn negative, which means it doesn't exist. So still look for both cases, the angle B and its supplement, then calculate what that would imply angle C is. If C is negative, then you're only going to have one triangle. If C is positive, like this example here, for both cases, then you're going to get two triangles. So you'll either have 0, 1, or 2 solutions in that ambiguous case. Okay, let's finish off with a couple of applications here. In this problem, we want to find the measure. To measure the height of a mountain, a surveyor takes two sightings of the peak at a distance of 900 meters apart on a direct line to the mountain. The first observation results in an angle of elevation of 47 degrees, and the second results in an angle of elevation of 35 degrees. So here's my picture. Here's your mountain. The surveyor stands some distance away and looks up to the top of that mountain, and that angle of elevation, which is the angle from the horizontal, which would be this down here, up to the top of that mountain, that angle of elevation is 47 degrees. Then he moves away 900 meters and looks up at the top of the mountain again, and that angle of elevation from this horizontal up to that peak is now only 35 degrees. What we want to try to figure out is the actual height h of this mountain. Now it does say here that the transit is 2 meters high. What is the height h of the mountain? So the transit is sort of just kind of like how far off the measuring device is from the ground. So this is 2 meters off the ground, so we're kind of elevated slightly off the ground before we look up to the top of our mountain. So we will need to consider that 2 meter transit height at the end, but initially you're not going to worry about it yet. We're just going to see if we can find out what this h is right here, and then in the end we'll worry about that transit height. Okay? So what's the first thing that we want to figure out here? Okay, so if we look at our picture, we're looking to find this h. And based on what we've been talking about in all of the examples that we've done today, we've been using the law of sines, which requires knowing an angle opposite and its corresponding side, an angle and its corresponding opposite side. So if we look at this h, we would kind of need to know its opposite angle, which we do over here, this 35 degrees. But if you look at some of the other sides of these triangles that are involved, the only height or only distance that I am told at all is just this little distance from here to here is 900. I don't know this distance, I don't know either of these hypotenuse sides, I don't know this side over here, so there's a lot of missing information. Now if this 900 is the only length that I actually know, notice that it is opposite this little angle up here. So if I'm going to use law of sines at all, then I'm going to need to know what that angle is so that I can know an angle and its opposing side. So is there any way to figure out this little tiny angle up here? Well, not immediately or directly, but you do want to notice that this angle right here is the supplement of this 47-degree angle right here because they form a straight line. So this little angle right here in green has to be 180 minus 47, which is 133 degrees. So that forces this obtuse angle to be 133. Therefore, this little angle up here in red has to be 180 minus 133 and 35, the other two angles in this little triangle on the left. So 180 minus 35 plus 133, and that turns out to be 12. So this little tiny angle up here in the corner is 12 degrees. So now that I know that, how am I going to use that? Well, it starts us off in our law of sines. We can now use sine of that little 12-degree angle over its opposing side, which is that 900. So that's two pieces of information that I know. But then the next question is, okay, well, what do I put on this side? And you have several choices here. You can do sine of 35 degrees over this side over here. That would certainly be okay. You could do sine of 133 degrees over this side over here. Both ways will work. So it doesn't really matter. You just need to pick a way and go with it. So I'm just going to go ahead and use that sine of 133 degrees over this side over here. I'm going to call it side C. And let's solve for this side C. Now you might ask, well, how is this getting me closer to finding h? Well, we're working our way there. We're just trying to find out some more side lengths so that we can eventually narrow it down to figuring out what h is. So let's find out what this side C is, and then we'll go from there. I'm going to cross multiply, and then I'm going to divide both sides by sine of 12. Then you would punch that into your calculator, and you get that C is approximately 3,165.86. So that's this side over here. Okay? So now that I know that side, how does that help me at all? Well, you have, again, options here. It's totally up to you how you want to do this. There's multiple solutions for how to get h, multiple ways to do this problem. You could notice that if we wanted to find this h over here, then I know the side, or excuse me, the angle across from it, which was this little 35-degree angle. So if we did sine of 35 degrees over h, and this again is now referring to this bigger triangle here, where this is that h, this is that 35 degrees, that proportion would need to equal some other angle side combination. So what do we know here? Well, we just found that this whole length here, which is this sort of hypotenuse, is 3,165.86. What angle is that side opposite in this bigger triangle? Well, it's opposite a 90-degree angle. So this would be sine of 90 degrees over that hypotenuse. So this is just one possible way to solve this problem, okay? I'm just showing you one possibility. But if I do this now, I have only one variable h, so this should be enough to find out what this h is equal to. Now notice that this is a right triangle, and what does sine of 90 degrees equal? It equals to just 1. So when I cross multiply, I get 3,165.86 times the sine of 35 degrees equals h times 1, which is just h. So punching this now into my calculator tells me that h is approximately, I'm going to round off to whole numbers here since we've got a lot of approximation error going on, 1,816. Now let's figure out if that's what our answer is. Okay, remember that this person with his or her measuring device was 2 meters off the ground. So the actual height of the mountain isn't just this h, it's this h plus that 2 meters distance from the ground. So all we have to do now is add in that transit height to get our final answer. So the height of the mountain is a total of 1,818 meters off the ground. So this is the ground level down here. Okay? Again, more than one way to solve this problem, but it would be a similar technique no matter which way you did it. Okay, one last example here. The navigator of a ship at sea spots 2 lighthouses that she knows are to be 3 miles apart along a straight seashore. She determines that the angles formed between 2 line-of-sight observations of the lighthouses and the line from the ship directly to shore are 15 degrees and 35 degrees respectively. So a picture here is absolutely important. We have 2 lighthouses that are 3 miles apart along a straight seashore. So here's lighthouse number 1, here's lighthouse number 2, here's my seashore that's straight, and these are 3 miles apart. Then we have this ship out at sea, okay, and it's spotting these 2 lighthouses. She determines that the angles formed between 2 line-of-sight observations of the lighthouses and the line from the ship directly to shore are 15 degrees and 35 degrees respectively. So here would be the line of sight to the first lighthouse, here would be the line of sight to the second lighthouse, and the line of sight, or the line from the ship directly to shore, would be this perpendicular right here. So it says that the angles formed between the line of sight and that perpendicular line are 15 and 35. And we don't necessarily know which one is which, but let's just label this one over here 15 and this one over here 35 degrees. So there's our picture. What do we want to know? For part A, we want to know how far is the ship from lighthouse A. So let's call this guy A and this guy B over here. So what I want to know is how far is this distance right here. Okay, so let's call that X and let's call this Y over here. So if we want to find out how far is the ship from lighthouse A, we want to know this distance X over here. So what can we do to figure that out? Well, we know these angles here, 15 and 35. We only know this entire distance 3. If I knew just this distance along the left right triangle, then you could just use your right triangle definitions for your trig functions to figure out what x is, using opposite over hypotenuse or adjacent over hypotenuse or something like that. But I don't know just this distance right here. I only know the whole distance is 3. So that whole distance 3 is opposite what full angle? It's opposite this entire angle all the way across, which is 15 plus 35, which is a total of 50 degrees. So if we wanted to use law of sines here, there is an angle and its opposite side pair that go together. So I could say sine of 50 degrees over 3 equals, and now we need some proportion over here, some ratio over here that's going to involve this x. So what angle, what angle is it opposite? It's opposite this one over here. So how do I figure out what that little angle is? Well, it's the acute angle in this right triangle. And if I know that this piece is 35, then that forces this angle to be 55. So I can use sine of 55 over x in my law of sines. So here's my proportion that I need to solve. So let's cross multiply. And divide both sides by sine of 50 punch it in your calculator, and you get x is approximately 3.208, and our units here, since it was 3 miles, this is going to be miles as well. So the boat is about 3.2 miles away from Lighthouse A. How far is the ship from Lighthouse B? So that's this distance over here, so this time we're looking for y. So we're going to do the same exact thing, but this time side y is opposite this angle over here. So if we look at this little right triangle, this angle is 15, so that forces this little acute angle up here to be 75. So side y is opposite angle 75 degrees. So we're going to use that in our proportion for law of sines. So sine of 50 over 3 equals sine of 75 over that y. Cross multiply. Divide by sine of 50. Punch it in your calculator, and you get y is about 3.783 miles. Okay? Then the last question is, how far is the ship from shore? So on my picture here, here's the boat, and here's the shore. So the distance between the ship and the shore is this horizontal right here, this h. Let's call it h. So we're looking for what h is. Now you can find h in many different ways. One way to think about it is it's this leg of one of these two right triangles, and it doesn't matter which one you use. So say that I use the triangle on the left side. Let's draw this picture over here. So we're looking for h. We know this little angle is 75, we know this angle is 15, and we know what this hypotenuse is because that was x, and we already figured that out to be about 3.208. We still don't know what this side is over here. But it's not going to matter because since this is a right triangle, you can use law of sines. It still applies. Law of sines applies to any kind of triangle, and you could do sine of 90 over this 3.208 equals sine of 75 over h. Or you could just realize that because this is a right triangle, you can just use those right triangle definitions. And if we wanted to use, say, a sine, then we know that sine is opposite over hypotenuse. So if I looked at this 75-degree angle, its opposite side is h, and its hypotenuse is 3.208. So sine of 75 has to be h over 3.208. And it would be exactly the same thing you would get if you had used law of sines, because sine of 90 goes to 1. So it's the same exact equation. So let me write this down here. We're basically just using the right triangle definition that sine of an angle, in other words, sine of 75, is the opposite side, which is what we were calling h, over its hypotenuse, which was that 3.208 that we found earlier for side x. And to solve this, we would just multiply that 3.208 over to the left side and punch this in your calculator. And when you do that, you get that h is approximately 3.10 miles. Okay? So law of sines, sine of a over little a equals sine of b over little b equals sine of c over little c. Find a combination, an angle and an opposite side that you know go together, that you know both of the values of, and that's going to be your starting point. And based on the kind of triangle you're given, whether you're knowing two angles and one side or one angle and two sides, you'll need to consider possibly having that ambiguous case of either 0 triangles, 1 triangle, or 2 triangle. So it's a lot of stuff to consider, but looking through all of the examples from this lecture, you'll see every possible case that might occur. All right, that concludes our lecture on law of sines. Good luck.